In this video, we are going to talk about quantum numbers, which are a set of numbers that characterize an electron and describe its state in an atom. In order to give you an idea of where these quantum numbers come from, we need to recall the Schrödinger wave equation. You know that if you have an electron in an atom, let's say here you have the atom, you have the nucleus, and you have electrons that orbit this nucleus, okay, in specific regions that are known as orbitals. The state of any electron in an atom is described by the Schrödinger wave equation, which relates the Hamiltonian of the system of the electron to its total energy. So usually that's written as H psi equals to E psi, where H is the Hamiltonian, psi is the state or the wave function, okay, of the electron, and E is the energy, the total energy. This video is not about quantum mechanics, so I won't go into the details of this equation, but the idea is that solving this equation gives us information about the electrons inside the atom, about their states, about their energy, about their orientation. To do this, we employ a technique usually known as separation of variables. So the idea is that we write the wave function, which is expressed in polar coordinates as r, theta, phi, as a product of functions that depend on each of the variable. So r for the size, theta for the angle, the polar angle, and phi for the azimuthal angle. When this is plugged inside this equation, we get a set of differential equations, okay? And the solution to those differential equations are the quantum numbers that you may probably heard of. 4 of them in particular: N, L, Ml, and Ms. Let's start with the first one of them, which is N. N is known as the principal quantum number. This quantum number indicates the shell in which the electron resides. You know, electrons orbit an atom in shells, just like bookshelves. And the higher the shelf, the higher the quantum number, thus the higher the energy. Or to say it in another way, the higher the shell that the electron occupies, the higher its energy, and the higher the quantum number, the principal quantum number. N takes integer values, positive integer values for that matter. So N can be 1, can be 2, can be 3, can be 4, etc. For example, the hydrogen atom has 1 electron, so N is equals to 1, and this corresponds to the ground state. The second quantum number, L, is known as the azimuthal quantum number, or usually known as the angular quantum number, because it is obtained by solving the equation that depends on theta. The angular or the azimuthal quantum number has as primary role that it determines the shape of an electron's orbital. The set of values that it can take vary from 0, okay, to n minus 1, which means that if n is 2, for example, then L can take values between 0 and 1. In other words, 0, 1 in this case. So various values of L correspond to various shapes. For example, if L is equal to 0, okay, then this corresponds to an s orbital, which is spherical in shape. If L is 1, then this corresponds to a p orbital, which has a dumbbell shape. If L is 2, this corresponds to a d orbital, which is shaped like a flower, like clovers, to be more precise. And if L is equal to 3, we get the last type of orbital, which are f orbitals, and which are much more complex. The third type of quantum numbers, ML, is known as the magnetic quantum number. This number specifies the orientation of the different orbitals around the nucleus. For example, if we take L equals to 1, which represents a b orbital, depending on how this orbital is oriented with respect to the different coordinate axes, we can have the px, which means it's oriented along the x-axis, the py, if it's oriented along the y-axis, or the pz, if it's oriented along the z-axis. And same goes for the other types of orbitals. And the last quantum number, ms, is known as the spin quantum number. You know that an electron doesn't just orbit around the nucleus of an atom, but it also has a spin, which is much more similar to just any rotating body. If you have a body that rotates, it has a spin axis, so does an electron. It's really an intrinsic properties of the electrons. The reason this is important is because it accounts for a very important property of quantum systems, summed up in a principle known as Pauli exclusion principle, which tells us that if you have two electrons that are in an orbital, a given orbital, if one has a positive spin, then the other one should have a negative spin. In other words, two electrons cannot have the same exact spin or the same exact quantum state in a given orbital. And that is the reason why this spin quantum number is important, because it accounts for that. So an electron that's represented like this in this electron in box notation would have a spin of plus half, and an electron, its counterpart, okay, would have a negative half spin. So this is really important, and it accounts for the Pauli exclusion principle. So let's now represent these different orbitals and see what they look like actually in space. So let me take another paper. Let's start with the first type of orbital, which are the s orbitals. As I mentioned earlier, an s orbital corresponds to an azimuthal quantum number L equals to 0. And L equals to 0 implies that the possible magnetic quantum numbers are m equals 0. So probably what I forgot to mention here, okay, is that the magnetic quantum number has a range of values from negative L to L. So m lies between negative L and L, which means that if L is 0, then m has to be 0, okay? In this case, we have just one possibility. So if here we have x, y, z, then the shape described by these quantum numbers is just a sphere, okay? And that corresponds to an s orbital. Moving to the next type of orbitals, which are the p orbitals. A p orbital, okay, has L equal to 1, as I also mentioned earlier. And if L is 1, knowing that M ranges from negative L to positive L, it means that the possible values of M, okay, are negative 1, 0, and plus 1. So in this case, we have three possibilities, which would correspond to the px, py, and pz orbitals. The way they look like, if you want to make a rough sketch, we said p orbitals had a dumbbell shape, so you can imagine something like this. In this case, the dumbbell are oriented along the x-axis, so this corresponds to the px orbital. If the dumbbells are oriented along the y-axis, like that, so let's say this is y, this is z, then we have the py orbital, okay? And the last type, if the orbitals or the dumbbells are oriented along the z-axis, like that, then we have the pz orbital. So this corresponds to m equals negative 1, this corresponds to m equals 0, and this one corresponds to m equals 1. So these are the different possibilities of a p orbital. And you can notice that changing the magnetic quantum number changes the orientation, which is the function of this quantum number. And of course, if the principal quantum number increases, then you are going to have the dumbbells that would be bigger, okay, but their shape, their orientation is not going to change. Moving to the next type of quantum numbers, of orbitals, I mean, we have the d orbital. The d orbital has as azimuthal quantum number L equals to 2, okay, which means that the d orbitals can only exist for elements that have at least a principal quantum number n equals to 3, because L varies from 0 to n minus 1. And for the d orbital to exist, L has to be 2, which means that this can only be possible for elements that have at least n equals to 3. If L is equal to 2, then the magnetic quantum number, you remember that the magnetic quantum number varies from negative L to plus L. So in this case, M has to be negative 2 or negative 1 or 0 or 1 or 2. So there are 5 possibilities. And these 5 possibilities would correspond to the 5 different types of d orbitals. So if we want to sketch them, let's say here we have x, y, and z. Recall that, as I mentioned earlier, the d orbitals are shaped like clovers, so they are just like flowers. So if you have the clovers that are along the x and y axis, if the leaves are along the x and the y axis, then in this case we have the dx2y2 d orbital, okay? Then we can have other possibilities, z. We can have the leaves, okay, which are between the x and y axis. So they are not along the axis, this time they are between the axis, so like that. In this case, this type of orbital is known as the dxy orbital. And then you can do same for the other axis if you understand the trick. So let's say here is z and here is y. If the leaves are within the x and the z axis, then that's just the dxz. Then you can also have the dyz, so you just have a y and a z, okay? If you have the leaves in between here, like that, you're going to have the dyz. And the last type, if you have the two leaves along the z-axis, okay, so you have a pair like this, and you have another pair, usually represented thus. In this case, we have the y-axis here, we have the DZ2. So these are just rough sketches. I might try to add pictures or images on the screen so that you can be following up the exact shapes of the different orbitals. And the last type of orbitals are the F orbitals. Okay? For an F orbital, L has to be 3. Okay? And if L is 3, it means that M can take values between +3 and -3. Okay? So in this case, we are going to have a total of 7 possible orbitals, which represent the F orbitals. They are much more complex, so I won't sketch them here, but I will try to add pictures on the screen or images that represent the different set of orbitals. So let's just take an example of an element and try to see actually what the different orbitals imply for a given state of an electron. So let's take an example, in this case iron, to illustrate what the different quantum numbers imply for an electron. So iron, you know, it's a transition metal that has an atomic number 26. So we can represent its electron in box notation or its electronic configuration. So that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. So that's 10, 18, 10, 18, no, 20 and 26. Yeah, that's fine. Okay. So you can see that in this example, we have electrons that have various principal quantum numbers. You have electrons that have principal quantum number n equals 1. There are 2 of them. Then you have these 2, okay, that have principal quantum number n equals to 2. Each of these, in fact, are known as subshells. Subshells are simply group of atoms or orbitals that have the same principal quantum number. So these 2 are known as subshells. And we have this 2 and this 1 that also form subshells, okay, because they have the same principal quantum number. So let's focus our attention on the 3D subshell, for example. As we mentioned earlier, the D subshell has 5 different orbitals, okay? So here, if we want to represent it using the electron in box notation, we need 5 boxes. So 1, 2, 3, 4, and 5. In this case, all the electrons that belong to the subshell have principal quantum number L equals to 3. There are 6 of them, so if you want to fill in the boxes, we need to do 1, 2, 3, 4, 5, and then 6. Remember, this is a consequence of Pauli exclusion principle, which tells us that 2 electrons cannot have the same exact quantum state in an orbital. If one is plus half, the other one automatically has to be negative half. That's why we have this. Since it's a d orbital, L in this case has to be 2. Okay, remembered we saw previously that d orbitals have azimuthal quantum number L equals to 2. The magnetic quantum number, on the other hand, has 5 different possibilities. It can be -2, -1, 0, 1, or 2. And actually, each of these different magnetic quantum numbers would correspond to a box here. So m equals -2 would correspond to this box, m equals -1 would correspond to this one, m equals 0, this one, m equals 1, this one, and m equals 2, that one. And lastly, the last quantum number, s can either be plus half or minus half, as we saw earlier. So all the electrons that have arrows pointing upwards, like that, would have s equals to plus half. And all the electrons that have arrows pointing downwards would have s equals minus half. For example, this electron here, this one, is going to have s equals minus half because it has an arrow pointing downwards. Okay, so this was just to illustrate with a more concrete example how the different quantum numbers relate and what they imply for electrons in various subshells or orbitals. Hope you find this video interesting. Hope it's helpful. If so, like the video, subscribe, and I see you in the next video to talk about another interesting topic.